Albert Einstein was the most famous scientist on Earth. His ideas reshaped reality itself. But years later, a younger physicist looked at Einstein's work and dared to ask a simple question. Not to attack him, not to replace him, but to understand what everyone else was afraid to question. What happened next wasn't a debate. It was something far more rare in science: respect. Richard Feynman's greatest contribution was not just in the equations he wrote, but in the attitude he brought to science. An attitude that insisted that no idea should ever be treated as untouchable. He believed that progress begins the moment we allow ourselves to question what seems established and secure. In his view, theories were not monuments carved in stone, but tools, temporary explanations waiting to be tested against reality. This mindset directly challenged the culture that often forms around great figures like Einstein, where admiration can quietly turn into intellectual fear. Feynman refused to inherit ideas simply because they came from a famous name. Instead, he took them apart piece by piece, rebuilding them from the ground up to see whether they truly reflected how nature behaves. That process of questioning was not disrespectful, it was essential, because nature itself does not reward loyalty to tradition, only accuracy. Feynman often warned that the easiest way to be wrong is to assume you are right simply because everyone else agrees with you. In science, consensus can create comfort, but comfort is dangerous. When ideas stop being questioned, errors become invisible, hidden beneath layers of agreement and repetition. Feynman understood that many scientific breakthroughs did not happen because someone was smarter, but because someone was less afraid to ask a question others had stopped asking. By challenging assumptions embedded in established theories, he exposed weaknesses that were not obvious on the surface. This approach helped push physics beyond classical thinking and forced deeper engagement with quantum reality, even when the conclusions felt uncomfortable or counterintuitive. What made Feynman's questioning so powerful was his commitment to understanding rather than winning arguments. He did not ask questions to prove others wrong. He asked them to find out whether an idea actually made sense. If a theory could not be explained clearly, he believed it was not fully understood, no matter how mathematically elegant it appeared. This insistence on clarity acted like a filter, separating genuine insight from impressive-sounding confusion. It allowed him to cut through complexity and expose where ideas rested more on tradition than on evidence. In doing so, he demonstrated that questioning is not an act of rebellion, but a method of refinement, sharpening theories until they either improve or collapse. This attitude is what allowed scientific progress to continue even when confronting ideas as powerful as Einstein's. Feynman showed that questioning does not diminish greatness, it extends it. Einstein himself had questioned Newton, overturning centuries of accepted thinking. Feynman simply carried that tradition forward, reminding the scientific world that reverence should never replace curiosity. By keeping ideas flexible and open to challenge, science remains alive, responsive, and honest. The lesson is clear. Advancement does not come from protecting theories, but from exposing them to doubt. The moment questioning stops, knowledge freezes, and discovery gives way to belief. The story of Richard Feynman and Albert Einstein reveals how deeply scientific understanding depends on the diversity of human thought, not just on intelligence alone. Einstein approached the universe through carefully crafted thought experiments, imagining himself riding alongside a beam of light or falling freely through space to uncover the hidden structure of reality. His genius lay in his ability to visualize abstract concepts in a quiet, almost philosophical way, allowing him to reshape our understanding of time, space, and gravity. Feynman, by contrast, attacked problems with playful intensity. He spoke loudly, thought visually, and treated physics like a puzzle that could be taken apart and reassembled. Where Einstein searched for elegant unifying principles, Feynman searched for mechanisms, how things actually happen. Step by step, in the real world, these contrasting styles were not a weakness but a powerful advantage for science itself. Einstein's way of thinking allowed him to see beyond the limits of classical physics, but it also led him to resist aspects of quantum mechanics that felt incomplete or philosophically unsettling. Feynman, growing up in the quantum era, was far less concerned with whether a theory felt satisfying and far more interested in whether it worked. He accepted uncertainty as a feature of nature rather than a flaw in understanding. His diagrams transformed dense mathematical expressions into intuitive pictures, making invisible particle interactions feel almost tangible. This visual, hands-on style allowed him to navigate areas of physics that Einstein found increasingly frustrating, not because Einstein lacked intelligence, but because his mental framework was built for a different kind of problem. When these two approaches intersected, they highlighted a crucial truth. No single way of thinking is enough to fully understand reality. Einstein's conceptual depth and Feynman's intuitive pragmatism each revealed different layers of the same universe. One focused on the structure of the cosmos as a whole, while the other explored the chaotic dance of particles at the smallest scales. Science advanced not by choosing one approach over the other, but by allowing both to coexist, challenge, and inform each other. This dynamic is what drives progress across generations as new thinkers reinterpret old ideas through fresh perspectives. Feynman's success demonstrated that innovation often comes from seeing familiar problems in unfamiliar ways. By translating abstract equations into simple mental pictures, he made complex ideas accessible not just to students but to fellow scientists. This ability to reframe problems exposed blind spots that more traditional approaches overlooked. It showed that brilliance is not defined by a single intellectual style, but by the flexibility to move between different ways of thinking. The deeper lesson is that understanding grows richer when diverse minds engage the same questions. When science embraces multiple perspectives, it becomes stronger, more resilient, and more capable of revealing the true complexity of the universe. One of the most powerful lessons from Richard Feynman's relationship with Albert Einstein is that genuine respect in science is not granted by reputation, titles, or seniority, but earned through clarity of thought and intellectual honesty. In many academic environments, authority can quietly replace understanding, allowing famous names and established theories to stand unchallenged. Feynman rejected this culture completely. He believed that an idea should stand or fall on how clearly it explains nature, not on who proposed it. When he questioned concepts connected to Einstein's work, he did so by stripping them down to their essentials, asking whether the assumptions truly matched experimental reality. This approach did not attack Einstein as a person. It honored him by taking his ideas seriously enough to test them. Feynman's clarity came from his insistence on deep understanding rather than surface-level agreement. He often said that if you cannot explain something in simple terms, you do not really understand it. This belief shaped how he interacted with the work of others, including giants like Einstein. Instead of being intimidated by complex mathematics or elegant formulations, Feynman focused on whether the ideas made physical sense. He wanted to know what was actually happening in nature, not just how to describe it symbolically. By asking precise, grounded questions, he exposed gaps between mathematical beauty and physical reality, gaps that only became visible when someone dared to question authority. Einstein, despite his towering reputation, recognized the value of this approach. He understood that science does not progress through agreement alone, but through careful challenge. Feynman's questions were not driven by ego or a desire to undermine Einstein's legacy. They were driven by a shared commitment to truth. That sincerity is what earned respect. In science, respect flows toward those who help us see more clearly, even when their questions make us uncomfortable. Feynman embodied this principle, showing that intellectual courage paired with humility is far more persuasive than status or prestige. This exchange highlights an essential principle of scientific culture: authority must never replace evidence. When authority dominates, progress slows, creativity fades, and errors persist unchallenged. Feynman's clarity cut through this danger by reminding the scientific community that nature is the ultimate judge. Experiments do not care who you are or what you believe, they only reveal what is true. By grounding his arguments in observable reality, Feynman reinforced the idea that respect in science comes from alignment with nature, not alignment with hierarchy. The broader lesson extends far beyond physics. In any field of knowledge, progress depends on the willingness to value clarity over credentials and understanding over reputation. Feynman's interactions with Einstein show that even the greatest minds remain open to challenge when it is offered honestly and intelligently. Respect, in its deepest form, is not demanded. It is earned through clear thinking, careful questioning, and an unwavering commitment to truth. At the heart of the interaction between Richard Feynman and Albert Einstein lies a lesson that reaches beyond equations and theories. Humility is the foundation upon which all true discovery is built. Despite being among the most brilliant minds in history, both men understood in different ways that knowledge is always incomplete. Einstein revolutionized physics by questioning Newton's absolute space and time, yet even he remained uneasy about quantum mechanics because it challenged his intuition about how reality should behave. Feynman, coming later, embraced this uncertainty not as a weakness but as a signal that nature was deeper and stranger than human expectations. What connected them was not agreement, but a shared awareness that certainty is often the enemy of understanding. Feynman was famous for admitting what he did not know. In a culture that often rewards confidence and definitive answers, he openly stated that doubt was not only acceptable but necessary. He believed that pretending to know more than we do creates illusions of understanding that block progress. This intellectual humility allowed him to explore ideas without fear of being wrong, freeing him to follow evidence wherever it led. Instead of forcing nature to fit elegant theories, he allowed theories to remain flexible, ready to change when experiments demanded it. This openness is what made his work so powerful and enduring. Einstein, too, exemplified humility in his greatest moments. His willingness to challenge Newton showed that even the most successful theories must remain provisional. Yet his discomfort with quantum mechanics also revealed how difficult humility can be when ideas clash with deeply held intuitions. This tension itself became productive, pushing later physicists to confront the philosophical foundations of their work. Feynman's approach did not dismiss Einstein's concerns, it reframed them, suggesting that uncertainty was not a flaw to be eliminated, but a fundamental feature of reality to be understood. The humility shared between these thinkers illustrates a crucial truth. Discovery does not come from defending beliefs, but from remaining open to surprise. Every major scientific advance has required someone to admit that existing explanations were incomplete. This willingness to stand in uncertainty, to say, "We don't fully understand this yet," keeps science alive and evolving. Without humility, knowledge hardens into doctrine, and curiosity fades into routine. The lesson extends far beyond physics. In learning, creativity, and even everyday reasoning, humility allows growth. It invites questions, welcomes correction, and transforms mistakes into insight. Feynman's legacy reminds us that the most powerful words in science are not declarations of certainty, but admissions of curiosity. By embracing humility, we create space for discovery, allowing the universe to reveal itself not on our terms, but on its own.